Hello and welcome to today's theory prep video. Today we'll be talking about undirected graphs. So what's the motivation for an undirected graph? Well, you can think of it sort of as a network. So let's say we're trying to model people and their friends. So maybe for each person, we'd make a little dot, which in a graph we call a node. So there's A, B, C, D, and E. And maybe person A is friends with person B and person E, and person D is friends with E and B, and maybe also A, and then person C is only friends with person E. And the cool thing about this is that this abstract structure can represent lots of things. It could represent cities and which cities have roads between them. It could represent networks in computer science. And so since it can represent so many things, it's nice to study them because if we prove results about graphs, well, then they'll apply for all of these things that we can model as graphs. So I encourage you to maybe try and think of some other examples for what graphs might be used for, but you can see that they're pretty applicable sort of algebraic structure. And so let's formalize the idea of a graph. Here in that definition 9.1, we do. An undirected simple graph is a set of vertices V and a set of edges E. The set elements of E are sets, where each set is composed of two vertices that are not equal to each other. So let's give an example below. Here, the graph is equal to first, and we often write the vertices and the edges as the tuple. So first the vertices are A, B, and C, and then the edges are first the set AB, which corresponds to this edge, and then the edge BC, which corresponds to this edge. And just a couple observations about the definition. One is that here we're defining undirected graphs. Directed graphs will have edges that have a direction. So from A to B would be different from B to A, and you could have one or both of those. And then the other idea is that our graphs are simple, which just means that they don't contain things like self-loops, which is an edge from a vertex to itself, or multiple edges from B to C. And so we'll study simple graphs in this video today. Great, so there are a lot of problems that you can investigate through graphs, but we'll start with a matching problem. So let's say you're some online tutoring service and you get students and they put in preferences for which tutors they want to work with, and tutors maybe put in preferences for what students they want or also what subjects they might be able to teach. So you're working with some constraints. And the end result is that the students are paying you. So you want every student to be matched up with a tutor who they can get services from. And, I've drawn an example graph below, but maybe what we can do is we can represent every student as a vertex and every tutor as a vertex, and we'll draw a line between a student and a tutor if and only if they're compatible, right? If the student requested that tutor and that tutor also has the skills necessary to teach that student. And what we want is basically to pair up every student with a tutor. So in this graph, we might pair these two students up, or this student and this tutor up, pair this student, this tutor up, pair these two people up, and this student, this tutor, this student, this tutor, and this student, this tutor. Right, so that's the end result that we want to get to, but just take a little bit of a digression here. This is a really interesting and unique type of graph, which we call a bipartite graph, because we can separate all the vertices into two sets, into the students and the tutors, and no edge goes between two tutors or two students. Every edge just goes between one student and one tutor. So to formalize this definition mathematically, we say a graph is bipartite if we can partition the vertices into two sets. Recall that partition means we split it up into subsets such that the union of those subsets is the entire set, but they're all disjoint. So really what it means is you split the original set up into different groups. And so in this case, we've split it up into the vertices up into two sets, and L and R stand for left and right, usually, such that every edge has one endpoint in L and the other endpoint in R. So here we split it up into students and tutors, and as we said, every edge goes between one student and one tutor. So that's just an interesting graph structure that if you have that structure, you can prove certain results about it. So it's nice to define that. And also, if you think about certain problems, often you'll end up with bipartite graphs. So it's nice to have that definition because it comes up a lot and we know some important cool things about it. So want to share that first. Now let's move back to the problem that we were trying to solve. So let's try to define mathematically what we're trying to do in the matching problem. So if you remember, when we matched up all the students and tutors in this example, basically what we were doing is we were picking edges. And we want to pick one edge for every student such that each student gets assigned a tutor that they can work with. And so we might define a matching then as a subset of the edges of a graph, right? If you have some graph V, then a matching is a subset of the edges. And then what is the other important constraint? Well, we don't want to assign a tutor or a student to multiple of the other. For example, this student here, we wouldn't want to pick both of these edges because the student doesn't need multiple tutors in our scenario. Additionally, we wouldn't want to pick both of these edges because we're assuming that tutors can only handle one student. Maybe they have like a full-time job as well, so they don't have that much time to spare. So another property of matching that we want is that no vertex appears in the matching more than once. And under this definition, we could pick like this edge and then this edge, and that would be a valid matching. And that makes sense. That is a valid matching of some students to some tutors, but it doesn't cover everything that we want it to. So we should add one more thing to the definition. So we'll say a matching covers any vertices that appear in it. And so in this case, we want a matching that covers all of the students, right? Because we want every student to be assigned to a tutor. So that's what we're going to be looking for. Great. So this problem is definitely hard. And so whenever you see a problem that you're not immediately sure how to solve, often a good technique is to sort of play around with some examples and try and build some intuition for how the algebraic structures you're working with work and brainstorm some proof ideas. So maybe an easier question is, what is necessary to have a perfect matching? Or in other words, when is it clearly obvious that we cannot have a perfect matching? So I drew an example above where we could not have a matching that covers all the students. So in this case, it's clear that we can't have this matching because there are 3 students who basically prefer only 2 tutors. And so there's no way to assign each of these students to a tutor because you'd have to assign tutors multiple students, which we know is a constraint that we can't violate. So we can maybe try and formalize mathematically this intuition that we have, right? What we're saying is that if we have a group of n students that prefers fewer than n tutors, we can't have a matching that covers the students. And so what do we mean mathematically when we say prefer? Well, this is definition 9.4. So we say for any subset S of the vertices, the neighbors of the set S, denoted usually n of S, are defined as the set of all vertices such that those vertices are connected by an edge to the elements in S. So in this case, if we take these 3 students as the set S, then their neighbors are these 2 tutors. So if we take any set of students, their neighbors are essentially the tutors that we were saying beforehand that they prefer, right? So this mathematical definition captures that intuition. And just to give another example, so it's clear what we mean, right? If we have this one student, because we could just take a subset of one student, then the neighbors of this student are just this tutor because there's only one tutor who they prefer. So that means sort of our earlier intuition for what would be necessary to build a graph was that in order for a matching that covers all the students, in order to assign all the students to a tutor, we need that for any subset S of the students, the size of S is less than or equal to the size of the neighbors of S. What we're saying here is that for any subset of n students, what we need is that for them to prefer at least n tutors. That was exactly why this graph didn't work, because 3 students preferred 2 tutors. And it turns out that this condition is actually also sufficient. What I mean by that is that if this condition is true, if every subset of students prefers at least that many tutors, then there exists a matching for all the students. And this is a really useful result, because you could imagine if you're this company, then now you know, oh, I can pair up all my students. Or you know, oh, I can't pair up all my students, and you know, I'm going to have to ask some tutors to tutor twice or stuff like that. So this is actually called Hall's theorem. And I've written the theorem out mathematically here. For G, a bipartite graph with vertices that partition into L and R, then there exists a matching covering L if and only if for any subset of L, the size of the subset is less than or equal to the size of the neighbors of that subset. Great. So remember that whenever we have an if and only if statement, we want to prove both directions. And so we're going to first prove the forward direction, and then we'll prove the backwards direction. The forwards direction says, if there is a matching covering L in this graph, then every subset of students prefers at least as many tutors. And how do we know this is true? Well, remember, whenever we're proving an implication, we assume P. So first, assume a covering, assume a matching. M covering L. And then we want to prove for any subset of the students that this is true. So then we're going to fix arbitrary subset S of the students. And now we actually know, so consider, let's say this is our S right here, a couple of students. Well, the matching assigns every student in S to a unique tutor, so we know that the neighbors of S are at least as large in size because of the matching. So we know that the size of S is less than or equal to the size of its neighbors. And so that completes the proof of the forwards direction. Now we're going to do the backwards direction. And the backwards direction is a little bit more complicated. And it gives us actually the opportunity to use a couple of the proof techniques that we've used, which is why one of the reasons we picked this proof to highlight in the video. First, what we're going to do is, we need to prove the backwards direction. So let's make sure we understand what that means. So what we're saying is that if it is true that for any subset of the students they prefer at least as many tutors, then there's a matching covering L. We get the result that we want. And we're going to prove this by induction on the size of L. So your first question might be, how do we know to induct on the size of L? And that's a really good question, because whenever you see a proof or you're reading through one, you should always think about, how did the author know to do this? And that'll really help you build your own proof doing skills. And in this case, if you're not sure what to induct on, you should just try things like the number of vertices, the number of edges, and you'll quickly see that some of those are not going to be fruitful, and that other ones will lend themselves to really clean proofs. So a little bit of experimentation here can go a long way. Great, so let's move on to the proof. First, we have the base case, which is that there is one student. And if there's one student, we know by hypothesis that that student prefers at least one tutor, so we just assign them to that tutor, and now we have a matching covering all of L since there's only one student. Now for the inductive step. The inductive step, what we're going to do is we're going to assume the backwards direction, right? So we're going to assume the thing that we're trying to prove for anything with fewer than or equal to M students, and then we're going to prove it for a graph with M plus 1 students, right? And we want to prove it for any graph with M plus 1 students. And we're going to do this by cases. So in case 1, we'll say that case 1 means any non-empty subset S of the students has where we're talking about a subset of at most M students has the number of students is strictly less than the number of tutors that they prefer. Case 2 is that there exists some non-empty group of students such that there are at most M students in S, such that the size of S is equal to the size of the neighbors of S. And so whenever you have cases, you should always make sure that they're exhaustive, right? Whenever you're doing a proof by exhaustion. And so here, the hypothesis guarantees us that for any subgroup of students, that they will prefer at least as many tutors. And so that means there's two possibilities. Either every subset could prefer more tutors, or at least one group must prefer the same number of tutors. So clearly the cases are exhaustive. And the hypothesis is really important here because it allows us to ignore the case where like there's a subgroup of students who prefers fewer tutors. And I think in the past we've done cases by exhaustion where it might be easy to see that you're sort of exhaustive, if you have the odd and even integers, but this is a little bit more tricky here. So it's a good example of when you need to look to make sure everything's exhaustive. So let's do the first case. In the first case, we assume that every non-empty subset of at most m students prefers a strictly larger subset of tutors. And if a group of students S prefers a strictly larger number of tutors, then we can also say that the number of tutors they prefer is greater than or equal to 1 plus the number of students, right? Mathematically, we can write size of S plus 1 is less than or equal to the number of tutors they prefer, because both the number of tutors and the number of students are integers. So a strict inequality, well, we can just add 1 to the left-hand side to turn it into a weak inequality. Great. And this suggests a proof technique. Remember, what we're trying to do is eventually use the backwards direction or the inductive hypothesis on a group of students of size m. But we have m plus 1 students right now. So let's just take an arbitrary student, S prime. We know by hypothesis there's some tutor that they prefer, so we'll just assign them to T prime. And now we want to use the inductive hypothesis on the graph with L minus S prime and R minus T prime, right? And we know the size of L minus S prime is equal to m, so we're good on that front now. We just need to show that for any subset of students, for any subset of, let's say, the remaining students, we'll call L minus S prime the remaining students, that they prefer an equally or larger number of the remaining tutors. And so let's let n prime of S denote the number of neighbors of S in R minus T prime. In other words, intuitively, this is the number of tutors they prefer out of the remaining tutors. And what we'll notice is that taking away T prime from the tutors at most decreases the number of tutors that a group of students prefers by 1, right? Because that in the worst case scenario, somebody preferred that tutor and now they can't access them. So we can write m prime of S is greater than or equal to n of S minus 1. And just moving the 1 to the other side, we can write the number of tutors that are preferred out of the remaining tutors plus 1 is at least as many as the number of tutors that a group of students preferred initially. So now, putting these inequalities together up here, we write that the number of students in a set plus 1 is less than or equal to the number of tutors they prefer out of the remaining tutors minus T prime plus 1. So we get rid of the ones on both sides, and now we have the relationship that we want to have, right? Now we know that every group of students prefers at least as many tutors in our new graph. And so therefore we can imply the inductive hypothesis and get a matching covering L minus S prime. We combine that with the edge from S prime to T prime, and since none of the two T's in L minus S prime, none of the students in L minus S prime are using T prime, we can combine the matching and it's still a matching. So now let's do the second case. In the second case, we suppose there exists some subset of at most m students, we'll call it X, such that they prefer exactly Y tutors. And I think it's helpful to draw it out here. So let's draw out the students, the teachers, right? There's some subset X here, there's some subset Y, and all tutors that students in X prefer are in Y. And this suggests, if we take kind of a similar approach as to case 1, that, well, M has at most M students, so we could apply the inductive hypothesis here. And then L minus X has at most M students, so we could apply the inductive hypothesis there to like L minus X and R minus Y. And that's exactly what we're going to do. So let's sort of do this mathematically. So first, we realize that clearly X has at most M students, so it checks out to use the inductive hypothesis there. So now we want to check that for any subset of students in X that they prefer at least as many tutors in Y. Well, we know any subset of students in X is a subset of students in L, so we know that they prefer at least that many tutors in all of R, but all the tutors that students in X prefer are in Y, so they must prefer at least that many tutors in Y. So that checks out, and we can make a matching in between X and Y. And now, let's try and make a matching between L minus X and R minus Y. Well, we want to show that for any subset of L minus X, that the size of S is less than or equal to, and again, we'll use n prime here of S. And here, n prime of S will indicate the number of neighbors of S in R minus Y, right? So it's just sort of like if we're considering the bottom half of this graph, where how many tutors would they prefer? And we want to show, right, that in the remaining tutors, since we already used all of the tutors in Y, that they prefer at least as many tutors in those remaining tutors. Great. So how are we going to prove this? Well, we'll suppose towards contradiction that this is not true. And what does it mean for this to be not true? Well, it means that there exists some subset of the students in L minus X such that those students prefer strictly fewer tutors in n prime of S. And here, let's denote n prime of S by S prime. So, we have some group students S here and some group of tutors S prime, and the students in S prefer the tutors in S prime. Well, I claim there's going to be a contradiction here because consider the overall neighbors in the entire graph of X union S. Well, we know the neighbors of X are all Y, like the X students in X all prefer tutors in Y, and students in S all prefer tutors in S prime. So we know the neighbors of X union S are just Y union S prime, right? That mathematically what we're saying here is the students in X union S prefer the tutors in Y union S prime. But the issue here is that X and Y are the same size, right? And and we know the size of S is greater than the size of S prime. So that implies that the size of X union S is greater than the size of Y union S prime. In other words, is greater than the size of the neighbors of X union S. And putting this intuitively, basically what we're saying is that the group of students X union S, they actually prefer a strictly smaller group of tutors in the original problem. And that's not possible since we're proving the backwards direction. We get to assume that every subset of students prefers at least as many tutors. So that's a contradiction. Hence, this is incorrect. And so our first statement that any group of students in the remaining students prefers at least as many tutors in the remaining tutors. And therefore, we can again apply the inductive hypothesis to get a matching here. Then we just add those two matchings together. Like there's a list of edges for X, list of edges for L minus X, and we can just put them together because every X is paired to a tutor in Y, every L minus X is paired to a tutor in R minus Y, and those are disjoints, so there's no overlap in tutor, and we can just list all of the edges in one long big list. So this proves Howe's theorem, and it was a good proof to go over because it used a lot of the skills we've discussed in the course, like induction and casework, and it's also a cool result because we took a fairly simple condition that we just came up as necessary for matching, and it actually shows that that's also sufficient.